All right, let me get started for today. I'm assuming you can all hear me.
I can hear you.
Okay, thank you. So we are going to continue our discussion of large file systems. And I'm just going to finish off by quickly explaining how parity works in a RAID array so that they're using this in RAID 5 and other RAID configurations to determine whether the data is actually correct or not. And it's actually a very simple approach. So this is maintained with exclusive OR. So given 2 bytes of data on, let's say, drives D1 and D2,
Hey, do you have a black marker? This is really hard to see.
and see this? Okay. Let me see, maybe. My other black marker died. Is that better?
Yeah, that is. Thanks.
Yep.
Okay. We'll see how long this one lasts. I might have to run out and grab one from the supply cabinet. Apparently they hid them all when people fled the building. And so I had to ask where they were, and I just found out this morning, so I haven't had a chance to walk down there and take one. I don't know why they hid them. Maybe they were afraid. Yeah. So just tell me this is not working, because this pen is almost dead, basically. So actually, just hang for a few seconds, and it should take me about like 30 seconds to get on there and get one. All right, I found a blue one that I worked on. We'll see. So given 2 bytes, there we go, on drives D1 and D2, and let me write these out again. D1 is going to be 1, 0, 1, 1, 0, 1, 1, 0, 1, and then D2 is going to be 1, 1, 0, 1, 0, 1, 0, 0. So the XOR of those two is going to be 1, 0, 1, 1, 0, 1, 0, 1. Okay. 1, 1, 0, 1, 1, 0, 1, 0, 1. Yep, that's right. And so what happens is that the XOR byte is stored on a separate drive.
Excuse me?
Yep.
For the last 4 bits, shouldn't it be 1001?
Exclusive OR? It should be 0101. I think that's right. 101101101.
Okay, maybe I'm just forgetting how exclusive OR works. I thought 1 and 1 on exclusive OR is 0.
Uh,
I'll go look it up again. I'm just.
I'll check. I'm pretty sure this is right, but if someone says like, yeah, I'll check.
Well, yeah, even in the example here, it's not consistent because in D1 and R2 in the first bit, it's 0, 1 is 1, and then in
Oh yeah, I'm off by 1 here. 1, 2, 3.
there's another one that also is 1 and 0 is now 0. So somewhere in one of them is wrong. It has to be wrong because it's not the same.
That's
Hold
right.
on.
XOR gate is high one. Only exactly one of them is 1. That's why it's exclusive.
Yeah.
So the third bit from the right, they're both WUDs. So that one should be a 0. And the fourth bit from the right is 1, 1. So it should be 1, 0, 0, 1 for this example.
Yeah, and I'm looking at my notes. I've got 9 bits for an 8-bit XOR. That's why that's wrong. So 1011. These are not right. So 1011 1001. Does that look better?
Yep, much better. Thank you.
Okay. Sorry, my bad. I'll have to do this by hand, but that's fine. So anyway, the XOR byte, when it's correct, is stored on a separate drive D3. Okay. And if any one drive, D1 or D2, corrupts, the missing data can be reconstructed from the good drive and the parity bit, parity byte, sorry. So for example, if we lose D2, we can exclusive OR D1 and D3 to recover D2. So you would do D1, which is 0, 1, 1, 0, 1, 1, 0, 1. And then D3, that's the parity drive, is 1, 0, 1, 1, 1, 0, 0, 1. And if you exclusive OR these two, you're going to get 1, 1, 0, 1, 0, 1, 0, 0. And 1, 1, 0, 1, 0, 1, 0, 0 is D2, right? So the way these things reconstruct on the failure of any single drive is that they basically use the parity information and the data that they do have in order to reconstruct the data that they've lost, okay? And so that's why it takes a long time when they lose a whole drive. Is because they're busy running around and every byte they're using parity information to reconstruct it. And so it'll work, but it'll take a while. It's also how you can detect corruption. So you can actually do parity checking and you can recognize, hey, wait a minute, if the parity checking on the 2 drives doesn't equal the parity byte that I saved, something's not right here. And so you can identify the fact that, oh, something's corrupt here. And I'm going to need to fix it, okay? And that's why I can only survive the failure of one drive. If both drives die, then you don't have enough information to do reconstruction. So, okay. All right. There are some additional types of RAID that we didn't talk about. So RAID 6, striped with dual parity. So that allows you to survive 2 simultaneous drive failures. There's a RAID 1 plus 0. Which is a set of RAID 1 drives themselves being bundled and striped. to build a mirrored RAID 0 array. Okay, and so those aren't very popular, but they do exist if you want more security in the information you're storing. So any questions about this before I move on to ZFS, CFS, ZFS? Okay. So this is the zettabyte file system. So this is one of the first file systems that added in dynamic scalability, plus a whole bunch of other things like snapshots and so on. And so it's sort of the precursor of something like GFS or HFS, which is why we're talking about it. So this was originally developed by Sun Microsystems. In 2004, and this was Jeff Bonwick and Matthew Ahers. Matthew Ahers is still around. I haven't. Jeff Bonwick must be somewhere or other. I don't know where he's at. How many of you? You can use yellow. How many of you actually know what Sun Microsystems is? Nobody. Okay, cool. It doesn't exist anymore, of course. Well, it does, but it's owned by Oracle. Did someone's going to say something? Yeah. So go ahead. I keep cutting you off.
I was just going to say, yeah, I've heard of them, and it's kind of sad that they don't exist. They're kind of like the guys that built most of the things that we've kind of adapted and used, it seems.
Yeah, it's true, actually. They were a really cool company. They were in Palo Alto, just at one end of the bridge in Palo Alto that goes over from the bay to the other side, the east side. Basically, I saw a Sun workstation, late 80s, early 90s maybe. And so they made these things, these workstations, and they were some of the first commercially available high resolution, sort of pixel addressable workstations that ran a windowed operating system on top of them. They ran X Windows, of course. And so that was their sort of claim to fame. And so for a long time, whenever we used Unix in a windowed environment, we were going to use an Sun Microsystems workstation. And so they went along for quite a while until Oracle bought them. Probably in the late 90s, early 2000s, that's what I'm thinking. And so I haven't actually checked, but so Sun Microsystems was Java. That was their deal as well. And so that's why Oracle sort of got some control on that when they bought them out. And so the reason Oracle bought them, I think, is because they were a software company and they were building BI, business intelligence systems. They weren't called BI systems back then, but that's what they were. And so basically Oracle wanted to marry their software database system with hardware so that they could sell you an all-in-one solution for your data center. And so they bought a hardware company in order to do that. So Sun Microsystems lives on. If you buy a fully integrated solution from Oracle, you're getting their actual hardware. It's just not called Sun Microsystems hardware anymore. And Sun used to have their own CPUs. I can't even remember what they're called now, but they had a chip design that they used to build their own CPUs. There are a number of companies like this. SGI, Silicon Graphics Incorporated, was another one that's gone now. I can't remember. I think Cray Microsystems bought them, actually, or the other way around. I can't remember, but Cray and SGI are integrated together now. SGI was the graphics workstation company, and so when I was learning computer graphics as a graduate student, we all used SGIs. There really weren't any high-powered graphics hardware available except for SGIs. So any graphics lab you went to was full of SGIs. And at some point, sort of commodity PC graphics cards became good enough. And so SGI started to disappear. I actually remember the first year I went to SIGGRAPH, which is the huge computer graphics conference that we have every year. And people were actually talking about how, like, I replaced my most recent SGI with a PC, or I'm going to do that. And I realized at that point, well, that's the end for SGI, basically. And so, indeed it was, which is also sad because it's sort of nostalgic, I guess, for someone like me. But things never stay the same, so. And so now you have in your pocket a phone that's probably, I don't know how many orders of magnitude more powerful than the machines I started learning how to program on, or even the machines from 10 years ago. So, yeah. Just think when you have kids, you'll have stories about back in the day when I had an iPhone, and they'll think you were old.
We had to actually type what we were thinking, right? Like that whole thing.
That's right. Yeah, exactly. Yeah, like we didn't have a chip we inserted behind our ear. So I'm still waiting for that day. So let's go, Neuromancer. You promised me a chip, man. Where's my chip? So anyway, now I'm sad. Oh well. So what's up with this ZFS thing? So it turned out that a single, what they would call a ZFS pool, could hold 256, they're called zebibytes. So we're not even there yet. We're at terabytes. This is 2 to the 78 bytes. That's why it was called the zettabyte file system, zebibytes. And a system, an entire file system, which is made up of pools, can hold 2 to the 64th Z pools, for theoretical capacity. Of about 5 sextillion zebibytes, which is 2 to the 142nd bytes. That's a lot, even by our standards. So for comparison, the number of atoms in the planet Earth is estimated to be approximately 2 to the 166. So it's not as many atoms as there are on planet Earth, but it's around that. And so, of course, you could never really have this much space if you think about it, because you'd have to build something physical to hold the 2 to the 142nd bytes, and there's not enough atoms available spare in the planet Earth to build that, probably. And so I think they really could argue that, at least if we're still living on the planet Earth, we're probably never going to build a file system that can reach this capacity. So people always worry about this, because you probably remember the famous statement by, it was Bill Gates, when they had a 640 kilobyte memory capacity for their system, and he said, you'll never need more than that. Yeah. And that was true back when he was saying that. It was a huge amount of memory, but not anymore. So ZFS attempts to remove the need for a separate volume manager. And file system. So it wants to bundle them all together. So traditionally, the volume manager is used to prepare one or more hardware storage devices. To appear as a single device. Managed by a file system. Okay, so RAID does this as well, or attempts to. So the idea is that you have a bunch of, like, let's think about it in practical terms. You would have a bunch of hard drives, and so you would use the volume manager to take those hard drives and prepare them so that they appeared as a single virtual drive to the operating system, and then the operating system would be running its own file system on top of that virtual drive, which is really a whole bunch of physical hard drives somehow bundled together and managed by this volume manager. Okay, and so ZFS is trying to sort of encapsulate all of that into a single operation. And the nice thing about that would be then you would have the ability to do certain things, like if you needed more file space, you would simply jam another hard drive into your hard drive rack, and the volume manager / file system should automatically recognize that, hey, a new physical device was just added, and integrate it directly into the available virtual space with nothing else being needed by the operating system. The operating system would just suddenly see, oh, we have more space than we used to. Awesome, I can start using that. And even with RAID, you can't really do that easily, but with ZFS, you can. And I should mention that with the follow-on systems like GFS and HFS, you can do that as well. And I think ZFS sort of prompted the idea behind that. So in ZFS, the basic storage, I guess we would call it unit, is a quote-unquote storage pool. We've already seen this. Or it's called a Z pool, a Z pool. Okay. So traditionally, a volume manager would be needed to virtualize one or more physical devices into a single virtual quote-unquote drive. So RAID, I just talked about that. RAID uses this idea to virtualize a whole bunch of hard drives into a single virtual drive that has certain capabilities depending on what RAID level you're using. So in the background, you're getting replication, you're getting parallelization, you're getting parity error checking and other things like that. But from the point of view of the operating system, it's just a hard drive, just like any other hard drive. It doesn't recognize that any of that's happening because the RAID, either software or hardware implementation, is doing all of that for it in the background, okay? So this unified view of the underlying hardware allows a file system to sit on top. Without worrying about the physical details of the hardware. So that's great because that means that any file system, NTFS, HFS plus, HTFS, just works. And it doesn't care whether it's actually talking directly to a drive controller on a physical drive or a RAID controller that's actually acting as a proxy between the file system and a whole bunch of hard drives. From the file system's point of view, everything's exactly the same. And it's irrelevant what's underneath it, okay? So ZFS is a little bit different than RAID because it replaces explicit volume management Okay. So in ZFS, unlike RAID, you don't sort of set up the hard drives into some RAID level and then start using them. That's not required. ZFS automatically aggregates all available storage devices into a storage pool. And the storage pool understands the physical details of storage devices. So these could be things like the hardware itself, the layout, redundancy, and so on. Okay. And presents as one large data store to the OS. Okay. So ZFS and its corresponding storage pool idea takes care of everything underneath the operating system. And so there's no volume management required, there's no setup required, and there's certainly no need for the operating system to understand anything at all about any of the physical properties, redundancy, layout, error correction, any of that kind of stuff that's happening underneath it. From the operating system's point of view, a ZFS storage pool just looks like a really big hard drive. And it talks directly to it with its file system, whatever file system that operating system happens to use, the same way it would to any other storage device. Okay, so that's the key virtualizing. Difference here being that you actually don't have to do any setup, and what that means is it's also easy to make dynamic changes because of the way ZFS is configured and designed. Okay, so a few advantages of that. So some advantages of ZFS. So one is that the file system is not constrained to a specific hardware device. Okay, so what that means is that the file system, actually, and we saw this happening, not because of the ability to work, but the ability to work well. So when solid-state drives came along, because of the way that they work and the way that the operating system had previously worked with traditional hard drives, there was a problem. Actually, there were a number of problems. And so it took quite a long time for these problems to be fully worked out, and that required actual changes in the operating system. So good examples are both Windows and Mac OS. Mac OS took longer than Windows, but they had to rewrite the file system so that if they were talking to a solid-state drive, they actually told the solid-state drive some additional information that they hadn't been telling to the physical hard drives because it wasn't required. But solid-state drives have a limited amount of writes, wear leveling, and other things. And so they actually need to know certain things about what you're doing to files specifically at a level of granularity that a hard drive wouldn't care about. Okay, and so that information wasn't integrated into the operating system for quite a while because it's actually tricky and dangerous to change your file system on an operating system, right? If you get it wrong and you blow up everybody's file storage, they're probably not going to be too happy about that. Okay, so with ZFS, because it's taking care of all of those details inside the actual ZFS system, the operating system never has to worry about any of that collisions, okay, which is good, actually. Yeah. Another example of this would be if some new storage device came along tomorrow that we didn't know about today. As long as ZFS integrated it into its system, then all the operating systems that were built on top of ZFS would have automatically had access to that kind of hardware. They would have had to make no changes whatsoever. In fact, people used to talk about the fact that you could include, for example, tape storage or other things like that inside of ZFS, ZPool, if you wanted to, and it would be slow, but it would work, okay? And the operating system wouldn't know that that was happening, except that things were slow. So also, file systems do not require predefined sizes. They can grow to use any available space in the storage pool. So the file system doesn't have to constrain itself, it just uses whatever's available, and it can ask the storage pool at any given time how much space is available, and that's potentially changing, but the file system doesn't care, okay? Doesn't need to care. And then, of course, related directly to that is that new storage is automatically detected and integrated into the storage pool. Making it immediately available. To the file system. So again, like I said, if you just took a hard drive and added it to a storage pool, the operating system would immediately think, oh, the file system just got bigger. I didn't think it was that big. And so it doesn't do anything. It just, when it goes to save stuff, the next time it goes to do a save, it realizes, oh, there's more space available than there used to be. Great. Okay. So those are some of the nice advantages of ZFS. Okay. So the way the Sun engineers talked about this, so Sun engineers equated ZFS to Memory in a PC. Okay, so if you think about it, suppose I have a PC and suppose I turn it off and add a couple of additional memory sticks, or I swap out a couple of memory sticks for bigger ones and I turn the machine back on. So I don't have to do anything. I just have to turn the machine back on and automatically the operating system says, hey, there's more available memory than there used to be and I'm going to use it, right? There's no need for setup, there's no need for any kind of virtualization, there's no requirements apart from a few constraints imposed by the motherboard about what kind of memory sticks I can put in there, you know, et cetera, et cetera. Certainly from the operating system's point of view, there's no constraints. And so they thought, why don't hard drives or physical secondary storage, why doesn't it work like that? Why can't you just add more information, more drives, and the system automatically recognizes them either when it gets turned back on or as it's running, right? So if I take a hard drive out of my machine now and put a new one in, can I just turn it on? Well, no, actually. I have to format it. I have to tell the operating system what kind of file system is going to live on it. It has to be set up for that file system and so on and so forth. And so these are the things that Sun engineers are trying to get around, okay? So ZFS also provided a few basic sort of capabilities, which I'll list but won't go into any detail about. But they're capabilities that other systems also provide now, and things that we like. So ZFS also provided, well, it had fault tolerance. Via journaling. Okay. So the way journaling works in general, and so you see this in database systems, almost all RDBMS uses journaling, and ZFS uses it as well. So in a normal file system, when you write new data to a disk, it'll overwrite old data that's previously been marked as deleted. In these journaling file systems like ZFS, that never happens. So once you write something to a disk, it stays forever. When you change something on a disk, what actually happens is that a transaction is recorded in the journal log to say that this byte in this file changed from this to this. And then the new byte is written somewhere in available space, and a representation of the file on the physical disk is changed so that it properly links together all the most recent pieces of the file. But you always have, in essence, all copies of the file from the time that you first created it up until now. All right? So what that means is that if there's some sort of corruption, it's possible for you simply to take the journal and rerun it from the point of corruption forwards to recreate the file state from its last known good state to the state that it was in when the corruption happened. Okay, that's how database systems work as well when they journal. The other nice thing is if you're doing journaling like this, you also can snapshot. So you can actually get back the file at some previous state because all you have to do is sort of run the journal backwards to get back to that previous state. So you have this ability to version the file system. And I think in ZFS, you normally had to do it explicitly. You could ask for it to be done at every certain point in time. So what would happen is it would sort of freeze a copy of the journal and the file system state and then mark it as frozen and then move forward from that. But you could never sort of go back and do something that would sort of corrupt that or change that frozen state. So you could version your file system repeatedly. And actually new file systems like the macOS file system uses journaling to do this now. And so does Windows, I believe, if you ask it to. And the reason why is because disk space in general has become so cheap that it doesn't matter that you don't reuse space. You can actually afford to simply use space and then say that space is never going to be available again because most people aren't filling up even a fraction of their hard drive. Okay. And so you can do this. There's usually provision for getting rid of the oldest versions of something if you actually do run out of space. But in general, that never happens. Okay.
So, Professor, I have a quick, maybe tangential question to that. So one of the things that I've noticed over the past several years with new models of computers is, maybe like 10 years ago, it was, you would get a laptop and it was how many just gigabytes just of raw storage space you had on the drive. But now it seems over time that they're like, hey, well, we'll just give you SSDs, but they'll be smaller, kind of with that assumption of like, well, people weren't filling it up. We created these huge drive spaces that people didn't use, and now people are streaming everything that they don't store it on their laptop anyhow. I don't know if is that connected with that? You think of like, oh, they're still not filling it up, but we can still reuse. I don't know. That's just a tangential sort of observation. I didn't know if you thought anything about that or see any correlation there too.
So we haven't talked much about SSDs, but so the reason why SSDs adoption started with laptops and then moved on to even now, I guess if you buy a machine from Dell, like I still tend to get a physical hard drive. It was all about cost, basically. So SSDs were super expensive, and so they couldn't really afford to give you an SSD that was even a reasonable amount of size until fairly recently. And so they started in laptops, which by their nature were expensive to start with relative to desktops. And so you're right in the sense that they recognize, well, people aren't using all of the available storage that they have, and they're definitely not using it really on a laptop. So if we give them less storage and charge them a little bit more, because laptops are more expensive and because you're not using them like desktops, we can probably get away with that and you'll still buy them. And so that's what they did, basically. So now SSDs come in pretty big sizes and they're actually not that expensive. So you can see that they're migrating to PCs, right? So when you buy a PC, a Dell PC, if you buy a cheaper version of a home desktop, I think by default they'll try to sell you an SSD in it. It's only if you start getting into the workstations or the higher end gaming configurations where they think you might need more hard space that they're going to try to sell you physical hard drive instead, because they can give you some number of terabytes, whereas probably like 512 gig or 1 terabyte is where you're topping out in a consumer SSD that you can afford to buy. Okay, that's going to change obviously, and so at some point we're going to switch completely over to SSDs, and physical hard drives will be like floppy disks, right? We'll remember them, but we won't use them anymore. Yeah, and so
or at least on like personal devices. It still seems like even in like the world of like enterprise storage systems, right? Like the ability to just use cheap commodity hard drives are still probably going to exist just because they're so cheap and you can get tons of them and just swap them in and out with all these, you got RAIDs underneath your NetApp drives that are expandable and configurable, and you just add more, So sorry, tangential conversation, but just
no, actually, this is
on the conversation of, well, they're not using it, but we can do all this other stuff with space. It's just kind of an interesting sort of discussion about it.
No, and we'll keep talking about this right now because this is actually something that we do talk about in the class, and it is important. And it's going to be important going forward. So I will tell you that 2 things that might be useful. So one is that you're now seeing the conversion from physical hard drive to solid state drive in desktop, right? So we started off, they were sort of these weird things that only people who are really into computers bought. Then they moved into laptops, and nowadays I don't think you could find a laptop that didn't come with an SSD, right? And if you went out and tried to buy an actual laptop physical hard drive, I think it would be really expensive relatively because they don't make them. Mm-hmm. So the economies of scale don't apply anymore. Now desktops are switching over to SSDs, okay? Mm-hmm. And I know for a fact, this is about 4 or 5 years ago, the server farms are still physical hard drive because of size, cost, configuration, but all of the server farm people are actually testing racks of SSDs because they know that they're going to switch over at some point. And so they're trying to get ahead of that and figure out what are the pros and cons going to be and what do we need to worry about if we're actually using these. So for example, there was huge concern about longevity of an SSD when they first came out, like how long are they going to last? And what we found out pretty quickly was that in a personal computer, you don't need to worry. It's going to last as long as you have that machine. Like it'll last 10 years, and you're not going to keep the machine 10 years. However, if you're talking about a server farm where the read-write sort of capacity number that's done over a fixed period of time is much, much, much higher, it is going to be a problem, right? And so they're looking at that issue. Of course, in a server farm, by problem it means the disk failed, and so they pull it out and put a new one in. So it's not a problem in the sense that it won't work. It's a problem in the sense that, oh, what's it going to cost us if we have to do this? How much more money is it going to cost versus the performance increase that we're going to get? So I have no, I'm pretty sure that server farms are going to go to SSD at some point. I don't know when that's going to happen. I don't think it's happened yet, but like I said, they're certainly looking at it. The other thing that I'll mention to you is that if you want the biggest bang for your buck in terms of performance versus cost, hybrid drive is the way to go. Okay, so you've probably seen these. A hybrid drive is a combination SSD plus physical drive. It's all integrated together on a single device that fits into a hard drive chassis. And so it's usually about 256 meg, maybe 512 megabytes of SSD space, so a really small amount, and then a terabyte of hard drive space. And so it turns out that what the hybrid drive does is it's got a very smart algorithm and uses caching to keep things that it thinks are going to be needed most often on the SSD part, and then everything else is on the physical hard drive part. And it turns out that if you jam that into, say, a Windows machine or a Mac machine, that the SSD part is just big enough to cache the parts of the operating system that are being used all the time off hard drive. And so it gives you a huge improvement in performance with just a very small increase in cost. And so the simulation numbers I saw, or the tests that I saw, said that if you went from physical hard drive to SSD versus physical hard drive to hybrid, hybrid will give you 90% of the performance improvement that an SSD alone will. And so there's no need to get a full SSD. A hybrid will actually get you almost all the way there for a much cheaper cost, because, of course, the cost of half a gig or a gigabyte of SSD space is incredibly cheap relative to getting a full 512 gig of SSD. So at least right now, if you want to get a really fast quote-unquote hard drive, but you don't want to pay for an SSD, just buy a hybrid drive and stick that in there. Yeah. The thing that bugs me about Dell is like they don't sell hybrid drives, because I think they know this. They want you to buy the whole SSD. So, or it's hard to get a hybrid drive configuration from them. So, all right, let me just quickly finish this off, and then we'll be done for the day. And so the second thing that GFS provides is self-healing. So all data is checksummed. Okay. And so ZFS can determine when data corruption occurs, and because it's doing journaling, it can almost always fix that problem. All right. And so that's completely transparent to you in the background. But every time you actually go to grab a piece of data, to read a piece of data, checksumming occurs and correction occurs if needed. And so from your perspective, the data just never corrupts. You don't know whether it's actually corrupted and fixed or it's fine. Okay. And there are something called RAID-Z configurations. And I'll be honest with you, I haven't looked too closely at this, and so I don't know all that RAID-Z provides to you, but it provides like extended abilities for fault tolerance and checksumming, basically, through mirroring. That's one of the things it provides. So if you really want this, you can get it. Although ZFS itself will give you, in almost all cases, fault tolerance and self-healing. And then there are also snapshots. And that's what I was talking about before, where you freeze the file system at some particular state as read-only. And what that means is that when you snapshot something, every time you read from the snapshot. You don't need to worry about anything. And then as you add more changes, those are just being added in as sort of modifications to the snapshot. Okay. So snapshots don't actually cost a lot of extra space. It's not like you're creating an entirely frozen version and then copying that frozen version and working on that. You know, you're creating a frozen version and it's frozen as read-only. So it's only when you make writes to that frozen version that you need to start adding more information to the drive. And so snapshots are fairly cheap to make. Okay. So what happened to ZFS? Nobody uses it. And like I said, macOS actually thought hard about using it, and they implemented, they had a beta implementation of it that you could try out. But they eventually went with their own upgraded version that came out a couple of years ago, and it's not ZFS. My impression was that ZFS, although very cool, was also very hard to implement properly. And so for people who are looking at this, it just wasn't worth the effort of doing that. Hard drives were getting so much bigger and they were getting so much cheaper, and people were already used to the fact that sometimes a hard drive failed, and you just live with that. There's a lot of things about computers that people are used to and live with that they shouldn't, and this was one of them. And so they just didn't bother doing it. And now that we have these sort of cloud arrays and large storage arrays, there's no longer any real need for ZFS. You can get everything it provides through something that already exists now. So a super interesting system, and I think a nice precursor, because a lot of the file systems that came after took inspiration from this, but ZFS itself never got any traction. And so I don't know of any actual commercial system that uses it right now. Yeah. All right, any questions about that? Any questions about anything? Okay, I think you're good to go. Have a good weekend. Stay safe, and I will see you on Monday. I've already put out the Zoom invitations for next week's classes. All right, I'll see you later.
Thanks, Dr. Healy.
Thanks.
Thank you.